Hello, welcome back to the Thin Films course. My name is Professor Carlos Tavares, and I am from the Center of Physics at the University of Minho in Portugal. And so in this second chapter, I'll be talking about one of the physical vapor deposition methods, which is thermal evaporation. And it's used a lot in the industry, for example, to coat the inside of the optics for the headlights of the cars. So this mirror surface that you have inside the optics is actually an evaporation of aluminum that forms a thin film, which is like a mirror. And most of the mirrors are actually also made by thermal evaporation. So I'll give you some insight on this evaporation process, the different types of evaporation processes, and how you can make this kind of deposition by evaporation. So as the name says, it's a physical vapor phase deposition. So, as in the case of sputtering, it's also a PVD method. Okay, so the first films deposited by evaporation were prepared by Faraday in the first, well, in the middle of the 19th century. But only after the Second World War was there a great investment in this technology for the industry. Basically, what you have in thermal evaporation, you have to have a crucible or a boat or a filament where you put a material which will be melted, and after melting, metal can go directly from the solid state to the vapor phase in the formation, or it can go to an intermediate liquid phase. And so you need a material that can be melted and that has a reasonable vapor pressure, and the resulting flux of atoms or molecules will be deposited onto a substrate that we want to coat. So here is this example. We have a crucible, and this crucible can be a tungsten bolt, for example. Then you have to put your evaporant material, the material that you want to melt and to transform it into a vapor. Then you have to have a substrate, a material, so an object or a material that you want to coat it with this vapor flux. And then for specific process conditions, you will have this thin film. So the topics that will be discussed in this talk will involve thermal evaporation processes, film growth by thermal evaporation. In the first chapter, so I have given you an insight on thin film growth. And basically, this thin film growth can be, has the same properties or has the same understanding as it can be grown by thermal evaporation or by sputtering or by chemical vapor deposition, atomic layer deposition. So the kinetics involving the intrinsic film growth are probably the same. So then I'll be talking about the implementation of thermal evaporation. I'll give you also some information on materials and sources for thermal evaporation. So what is thermal evaporation? On both of these figures, like on the right, you will see there are two types of evaporation processes. The one on the left is perhaps the simplest one. It's a thermal evaporation using a crucible which is heated by a filament or by a resistance. So in this case, you need to have a heater. Then you have a crucible where you put your evaporant material, your target material. Okay. Upon heating the evaporant material, and after it reaches its melting temperature, then it will gradually evolve into a liquid phase or directly to a vapor phase. And you will have a flux of atoms that will leave the crucible and will be deposited as a thin film on your substrate. So you really need to have vacuum inside this process, okay? You need a vacuum system. Otherwise, these evaporated atoms or molecules will collide with the molecules of the gas from the residual atmosphere, and therefore the energy of these particles, these yellow particles, will be reduced from these collisions. So you will need to evacuate this chamber so that the main free path of these particles will be large enough comparable between the distance of the crucible to the target surface, in order that the particles may reach the substrate with the sufficient energy so they can nucleate, they can behave as atoms which can run all over the substrate to find the best nucleation sites possible to nucleate and grow the thin film, according to the thin film growth mechanism that I showed you in the first chapter. And on the right side, it's a similar system, but the material, it's not evaporated by means of a heater. So what we have here, and I'll show you more on that this process later on in this talk, is that we have an electron beam. This electron beam is produced and has a very high energy, and when it impinges on the crucible where the evaporant material is, it will melt it, and then this evaporant material will reach a vapor phase and will be evaporated and will condense on the substrate. Here, in order to produce this electron beam, you need a filament, so you need a cathode source. It can be, for example, a tungsten filament, which you apply specific voltage. You will inject electrons, and so in order that the electron will have this curvature that you see here, you need to have a magnetic field, and you will use Lorentz equation, which is the magnetic force equals the velocity times the magnetic field in vector notation. And so since the magnetic force is perpendicular to the plane created by the velocity of the electrons and the magnetic field, the electrons will describe this circular trajectory and will impinge here on the crucible and will heat up the source. I will show you a small video later on which will elucidate much better this process. So in most of the systems that have a thermal evaporator using a resistance, what you have is this kind of filament or a basket where you put your evaporant material, and the filament is heated as the current will pass through the filament. It has to provide a temperature large enough to melt the material, which is put here in the basket of the heater, and then this material, when it will be evaporated, it will have a flux that will condense onto a substrate. Normally we have here a shutter. It can move back and forth, so we can protect the substrate holder, because initially we might not want to start the deposition immediately. We just want, for example, the particles to thermalize and have sufficient energy. After a few seconds, then we will open the shutter. We also have here a quartz crystal balance, which will monitor the film thickness. In some cases involving thermal evaporation, the uniformity in thickness of the thin film is not very homogeneous. It has to do with the fact that when you have a material and it's being evaporated, it evaporates in all directions. So here you have a material which is being evaporated, for example, by the electron beam that I showed you a while ago. And so you have a flux in all directions. So which means that and since imagine that your substrate is here, so the material that you want to coat is here, okay? So you have a preferable flux of atoms that come from a normal incidence, okay? And therefore you will have some kind of curvature on the overall thickness of your film, which means you will not have a uniform thickness, but you will have something like this, okay? So in order to avoid this kind of inhomogeneity in thickness, sometimes it's better to introduce some gas in the process. You can have a gas inlet which will introduce some argon, and this small amount of argon is really important, for example, to make some collisions with evaporant atoms or molecules, so that they will scatter a bit and hit the surface in a more uniform way, and therefore provide a more homogeneous in-depth thickness. Furthermore, and as presented here, you can also introduce an ion source. This ion source has the sole purpose of bombarding the substrate surface with argon ions. And these argon ions, when they hit either the substrate surface or the film growing front, they will introduce some defects. And these defects, as we saw in the first talk, are very important for the atoms when they reach there to have locations which they can nucleate preferably. So, you know, as I mentioned, atoms will have some mobility to cover the surface, but they will nucleate on defects that are on the surface, for example, on impurities, on protrusions, or discontinuities on the sample surface. And if you impinge these very high energetic argon ions, they will create some defects here on the surface. And these atoms, when they reach there, they will grab this surface. It's just like if you're riding a bus and the bus is empty and it accelerates very fast, you try to hold on to something, otherwise you'll fall. And you want to stay in the same place. So these atoms will also want to grab a position so they can start nucleating the glowing film. So in most of the cases, before doing the deposition, you really need to have a high vacuum, which means you can have something in the order of 10 to the minus 4 to 10 to the minus 6 millibar. So if we look at 10 to the minus 4, that's actually a pressure which is 10 million times lower than atmospheric pressure. Normally, in our case, in our laboratory, we expect to have something 10 to the minus 6 millibar. And 10 to the minus 6 millibar, it's 1 billion times lower than atmospheric pressure. And this means that for this very low pressure, the atoms can have a very large mean free path. It means that these evaporated atoms, they can travel distances between 1 meter and 1 kilometer, okay, at this kind of pressure. So the lower the pressure you have inside the chamber, the lower is the probability for these atoms to collide. And so the lower the pressure, the larger will be the mean free path. So this is basically what I have been saying on the last slide. But now let's talk about vapor pressure. Evaporation occurs when atoms or molecules of the material being evaporated achieve sufficient energy to overcome the solid-liquid binding forces and enter the gas phase. So to increase the evaporation rate, the average energy is increased by raising the evaporant's temperature. That's why you can either, for example, if you use a crucible which is thermally heated, you have to increase the current that passes through the filament, or you have perhaps to increase the current of the electrons from the electron beam that impinges on the crucible. So expressed in another way, raising the temperature increases the evaporant's vapor pressure. And this is what we really have to look at when choosing a material that you want to thermal evaporate. So it's a common misconception that the solid has no vapor pressure, but as it melts, vapor suddenly appears. Well, melting has nothing to do with vapor pressure. For all materials that do not decompose, the vapor pressure versus temperature is a smooth curve, and I'll be showing you these curves. It's this kind of curves that you see here. For several elements you will have here, the vapor pressure either in units of torr or millimeters of mercury, or in bar. There's lots of units to measure pressure. You know, you have bar, you have Pascal, you have atoms, atmospheres, you have size, you have millimeters of mercury, torr. So there's a lot of units, and in the international system, we use Pascal, but in some industries, they for the position they recur a lot to the torr unit for measuring pressure. In my case, in the type of thin films that I produce, we normally work using the bar unit or millibar unit, subunit actually. So for all materials that are not composed, the vapor pressure versus temperature is a smooth curve, like I said, with the material's melting point at just one point on that curve. Okay. The Honig and Kramer's vapor pressure data for liquid and solid elements, which was published by RCA in 1969, really shows the non-relation between vapor pressure and melting point. So the most striking examples, and you have a lot, if you look at these two charts that I'm going to show you, there are some really interesting uh, facts you can compare between pairs of elements. And I'll be showing you some of them. So the most striking examples are two pairs of metals. For example, gallium and gadolinium, and also magnesium and aluminum. So the first pair, if you look at gallium and gadolinium, you have to know that gallium, it actually melts just above room temperature at around 30 degrees C. Gallium melts and starts to evaporate. So you can have, if you heat your room up to 30 degrees centigrade, and you have some gallium inside the glass, and you put, for example, a cover glass slide on top of this glass, then you will have a thermal evaporation of gallium that will coat the underside of the substrate. So you are actually making a thermal evaporation, but at a very low temperature, at room temperature, okay? So gallium has a melting temperature of around 30 degrees C, and gadolinium is about at 1,312 degrees C. Yet their vapor pressures are only within a factor of 10 for a large range of pressures. So it means that despite one of these metals having a melting point of around 30 degrees C and the other one 1,300, the vapor pressure difference between them is only by a factor of 10. It's very small, okay? But now if you look, for example, at aluminum and magnesium, they have melting temperatures around 650 and 660 degrees C. However, the magnesium vapor pressure is almost 10 million times higher than aluminum's at any temperature, okay? Despite having almost the same melting point. And this is what I'm going to show you, okay? So here you can look at aluminum, for example, and at these metals here, molybdenum, tantalum, and tungsten. And what they have in common is the pressure which they are indexed to now in this chart. So let's make an approximate reading here of the pressure with 10 to the minus 9 bar, okay? So, but you have to note that these elements, they have a vapor pressure of 10 to the minus 9. These ones here, in this oval here, when they're about 1,800, 2,200 degrees C, okay? So this vapor pressure for molybdenum, tantalum, and tungsten is similar to that of aluminum, but only when it's evaporated at around 800 degrees. So clearly, you can see that from these four metals, you can see that these three here, molybdenum, tungsten, and tantalum, have the same vapor pressure as aluminum, but at a temperature which is almost, well, it exceeds the doubling of the temperature for aluminum. So it means that what you can conclude is that these metals here, they really evaporate very little, okay, if at the same temperature that aluminum is yielding this vapor pressure, because you would really have to follow these curves down until you would reach 800 degrees to see the relation between vapor pressure of these metals, okay? So and another comparison, if you look at aluminum and it's around 800 degrees, and there's a vapor pressure of 10 to the minus 9, and if you look now at the comparison with magnesium, and magnesium has a vapor pressure of around 10 to the minus 9, but at a temperature of 250. So how can you compare this? Magnesium has a vapor pressure of 10 to the minus 9 at the temperature which is about 1/4 of the temperature of aluminum to produce the same vapor pressure, okay? So that's why magnesium, like as I mentioned before, has a vapor pressure which is 10 million times higher than aluminum. Another thing that it's important to note is here the case for lead and for tin. You know, perhaps you have seen people soldering electronic components. And in order, for example, to solder a capacitor or a resistor or a transistor in a PCB circuit board, you will need to have a soldering iron, and you need solder to connect these electronic devices to the PCB board. And one inconvenience of soldering is that the solder actually is not 100% composed of tin. So you also have some lead. And it's very important that when you're soldering, you wear a mask in order to avoid inhaling lead fumes, because these are very bad for your lungs. And if you compare, for example, here, we are seeing tin and lead at a temperature around 800 degrees. And you can see that if you look at the vapor pressure difference, it's about, here for tin is 10 to the minus 8, more or less, for lead 10 to the minus 4. So we have a vapor pressure of lead which is more than 10,000 times greater than that of tin for the same temperature. And it's really very crucial that you not inhale these fumes. So there is a strict relationship between vapor pressure and temperature. For each evaporant has at least one important consequence when evaporating alloys or mixtures. Except in rare circumstances, it's impossible to evaporate an alloy, so to have this alloy in a source and make a film with identical stoichiometry, because the components of this alloy, they will have individually different vapor pressures, okay? For example, when you try to evaporate 20% of tin and 80% of lead solder, it will almost initially give you a film with a much higher purity and concentration of lead, because the vapor pressure is 10 to the, it's about a million times higher than that of tin, depending, of course, on the temperature. So, and also when you evaporate compounds, there are also some general rules that you have to understand. Some compounds, like for example, magnesium fluoride or potassium iodide, they evaporate as molecules, and the film stoichiometry is identical to the compounds. But these are exceptions, okay? Oxides, they may dissociate completely. They can evaporate as lower oxides or evaporate as non-stoichiometric oxides, or give films with compositions identical to the evaporant. Compound semiconductor materials, the so-called 3,5, from the group 3,5 or from the group 2,6 materials, they present a complex mix of results. So individual components may evaporate as dimers or tetramers, depending on the temperature. Again, these compounds really need an in-depth understanding, and perhaps you should read the literature when trying to understand the kinetic evolving evaporation of this kind of mixed oxides or mixed constituents of the groups 3,5 and 2,6 materials. So when we're looking at the growth of evaporated films, we have to follow specific steps. Step 1 regards the production of species to be deposited. So we have to have a crucible. We have to have a way that we can heat or have an electron beam to melt the species that we want to evaporate and to be deposited. We have to provide sufficient energy and kinetics for these species to go from the source to the substrate. And then we have the nucleation of the film on the substrate. And all of these steps are independent, and they have their own characteristics and their own physical chemistry knowledge that we have to understand. So let's look at the first step, which is the production of species to be deposited. So normally, like I mentioned, these involve the transition from a condensed phase to a vapor phase. We can have the formation of compounds, the reaction between the elements of the compound, some which will be introduced in the chamber as a gas, or in the case of a vapor form. This means that, for example, I'll give you an example. For example, here, imagine that you are making evaporation of aluminum. You have some aluminum grains, metallic grains here, or metallic powder, or pellets, metallic aluminum pellets that you have in this crucible. And if you don't add any gas, you are just evaporating aluminum, and you'll have an aluminum film. But if you have a way to introduce a small amount of oxygen gas during this process, the aluminum will bond chemically with oxygen, and then you have a resulting alumina film or aluminum oxide. So instead of oxygen, if you introduce nitrogen, you then aluminum will bond to nitrogen and form aluminum nitride, which has a hexagonal structure. It's interesting material as a dielectric, for example, for making dielectric materials in some electronic devices, such as TFTs, for example. Now, let's look at the transport of the species from the source to the substrate. We can have different types of flow depending on the pressure, okay? It's really important maybe to always to have a knowledge of what the pressure represents in respect to the pressure that we have here in this room. So in this room, we have a pressure which is 1 bar, okay, very close to 1 bar, 1 atmosphere, or 100,000 Pascal, something like this, okay, or 760 millimeters of mercury. So when you are looking at the pressure inside the chamber, then the deposition, you have to think of how it relates to this atmospheric pressure that we have. So if we take into account that we have a pressure here which is 1 bar, and if we are making the deposition which is around 10 to the minus 3 millibars, so this is actually 1 million times less than our atmosphere that we're breathing in, okay? And the molecular flow that you will have for this range of pressures actually provides a very large mean free path for the particles, which means that the evaporated atoms and molecules, they can travel a long distance between the source and substrate, okay? And without having any collisions, so without losing their energy, okay? If you have a pressure which is 10 or 100 times larger than this case that we saw here, then the flow will not be molecular, will be viscous, okay? So it means that the flow will have to encounter some viscosity forces as the atoms or molecules travel from the source onto the substrate until the substrate, okay? So, and this normally involves higher partial pressures, something like 100,000 or 10,000 times lower than atmospheric pressure. And in these cases, it's because an inert gas is intentionally introduced in the chamber. And it's the case where I mentioned where you have sometimes you need to introduce some gas into the chamber, not to make a reaction, because, you know, if you want to make a reaction with the evaporated atoms or molecules, then you have to have a reactive gas like oxygen or nitrogen, okay? Or even a carbon source like methane or acetylene. But if you want to really have an inert gas in order to provide a uniform thickness, because this inert gas like argon or oxygen or krypton, they will collide with the evaporant flux and will normalize or homogenize the distribution of impinging atoms and molecules on the substrate, and you will have a more uniform thickness growth of your film, okay? And then, of course, then you will have to have higher pressures and you will have a viscous flow. So the third part is actually more related with what we learned on the first time. So it's the growth of the film on the substrate. The first initial stage of nucleation, which can be layer by layer growth, as we have seen, or can be island growth, or can be a mix between both, okay? And normally the energy of the incident species is between 0.5 and 1 electron volt for the case of evaporation, and 10 to 500 electron volts for the case of sputtering. So you'll see that, what does this really mean? This means that in the case of thermal evaporation, the atoms or molecules that hit the substrate here, they have a very low energy, which is about less than 1 electron volt, which is the charge times the voltage, okay? So it's the potential energy, or Coulomb potential energy. It's a charge times the voltage, and so it's less than 1 electron volt. And if you compare this with sputtering, which I'll be giving you some insight in chapter 3, this can be 500 times less than the case of sputtering, which means that the particles will not hit the surface with a lot of energy. Actually, the energy is very low, and so these atoms will not have a lot of energy to look for the best position to nucleate. So this is actually one of the disadvantages of thermal evaporation. The energy is very low of the impinging atoms or molecules, which means that the films will not have a very high density. They will not have a very good adhesion to the substrate. They have a relatively moderate low adhesion to the substrate. Sometimes you can scratch with your fingernails, you can scratch, lift off the material from the surface. Okay, in comparison to sputtering, for example, as I will show you in the next chapter, where these for specific cases, for specific films, especially when you make the deposition on them of these materials like titanium nitride on cutting tools, the adhesion is very strong, and you have a film which is very tough mechanically, which can have high hardness, have a high Young's modulus, or very high modulus of elasticity. Okay? And this, of course, is related to the energy of the impinging particles. And also the substrate temperature really is very important also for the nucleation of the film. You really need a sufficient substrate temperature to give some conditions for the thermodynamics to develop and for the film to nucleate on the surface. But if the receiving surface, if the substrate temperature is very high, then there's also the possibility of these particles being reflected, and they will not contribute to the growth of the thin film. So all of these things will impact on the structure, the composition, and the residual stresses of the films that we produce using this method. So in a thermal evaporation system, you really need to have a vacuum chamber. You have to have a vacuum system. You need a substrate holder, can be heated or not, preferably heated. And you need evaporation sources, where you put the material that is your evaporant, and you want to evaporate it. Okay, so it's the source that is used to heat the solid or liquid and transform it into a vapor phase. The choice is dictated by the material who one wants to evaporate, and also the desired rate of evaporation. So it means that for certain elements or compounds that we want to evaporate, we have to choose which type of evaporation source is more appropriate. Okay, we have to avoid contamination and ensure, as far as possible, the purity of whatever is deposited. And I'm going back to that chart that I showed you a while ago, because there's more information hidden here. For example, if you want to evaporate aluminum, you start off with some aluminum pellets. I'll be giving you some examples later on. Okay, and you have to think of which material can be the crucible for aluminum. But well, you can use a crucible made of molybdenum, tantalum, and tungsten, because for this same vapor pressure, they really have to be at different temperatures. So if you want to, in other words, if you want to evaporate aluminum, you just need to heat the crucible at a temperature of around 660 degrees C, or just slightly above it. Okay, and 600 degrees will yield a vapor pressure of aluminum of the order 10 to the minus 9 bar. Okay, you don't have to worry about contamination between aluminum and tantalum and tungsten, because these elements will not be evaporated very easily from the source, because they would only evaporate at temperature higher than 2000. Okay, and you're working at below 700 degrees C. Okay, and so these materials if you take a look, if you would have another kind of these graphs that would show you the vapor pressure of molybdenum, tantalum, and tungsten at around 800 degrees. So you have to follow these lines down until they would intersect this 800 degrees temperature line. You would see that the vapor pressure would be very, very low and insignificant in comparison to that of aluminum at around 800 degrees. Okay. And this is where we're heading now. So we're going to take a look at evaporation sources. So the mixture of evaporant and crucible has to be avoided. Okay. because then if you choose the wrong crucible, then you will have a mixture of the elements from this crucible and those from the evaporant, and you will be evaporating a compound, which is something that you do not desire. So you have really to choose very well which kind of crucible for the specific evaporant material that you want to use. Some chemical reactions involving the chamber components tend to produce also volatile contaminants, like iron oxides, which are ultimately incorporated into the film. You also have to avoid putting polymer materials inside, because if you're working at high temperatures, then the polymer materials start to degrade, and they will release a lot of gas. So they will degas, and this gas will contribute to the flux. So in order to choose the evaporation source, you need to consider the power density, which is required to evaporate the specific material. So you can melt these evaporant materials using different methods. You can use heated resistors. You can use heated systems by induction, like some, you know, in the kitchens. Perhaps some of you already have this kind of induction stoves. These induction stoves are this kind of ceramic plates that you have in your kitchen, and where you can cook, and you can put your hand, for example, on these places where you heat your food, or you put, for example, the pans, and you will not burn your hand, because the heat is provided by induction, which means that you have to have special pots and pans with a ferromagnetic bottom, which you can put on these kind of stoves, which are heated by induction. And so it's how does it work? Well, you have a magnetic field which fluctuates in time and induces the current in the bottom part of the pot or the pan. And this current will circulate in a medium, which is a ferromagnetic material, which has this specific resistance. So the electrons which are moving around in this bottom part of the pan or the pot, they will release energy when they collide with the atoms of the ferromagnetic material at the bottom part of the pot. For example, the pot or the pan can be in aluminum, but the bottom part has to be ferromagnetic. Okay, otherwise it will not be heated on an induction stove. Okay, so this is the basic principle. And also you can use this kind of heaters for melting these materials. You can have also another possibility of using an arc discharge or electron beam, as I mentioned before. And here are some resistive metal evaporation sources, which can be, as I showed you before, they can be made from, for example, tungsten, molybdenum, and tantalum, because they have a very neglected vapor source at very high temperatures. Okay. For example, if you look at, for example, if you compare, for example, carbon with these elements, you see that there's a variation of 6 orders. Okay, so the evaporation of carbon is a million times much higher than that of molybdenum, tantalum, tungsten at around the same, more or less the same temperature. So these are the kind of sources or boats. You can put your evaporant material, for example, here in these dimples or in these throws that you see here. Some of these actually evaporation sources are boxes which have some kind of pinholes, or these crucible holes that you see here, or they can be filaments or basket filaments in which you need to put a ceramic cup with evaporant material. So, and these evaporant materials, they can be aluminum, copper, silver, lead, etc., depending on the application that you want to use. Okay, for example, if you want to produce a mirror, then you need aluminum. If you want to make some, for example, I have some experiments with the students where we work with some polymers, and we add some metal particles onto the polymer when it is extruded, so that the polymer can become more conductive. So in order to measure the electrical properties of this composite, we need to have the position of metal contacts, and we can either evaporate aluminum or copper, for example, or silver. Okay, and then we will have the contacts to measure the resistivity of the composite material. This is just an example. Okay. So these boats here that we saw here are also shown here. So you have different types, and normally they are connected to both edges, which are the cathode and the anode of your system, where a DC current will pass through these boats, and the current will heat up the boat or these boxes until it reaches the melting temperature of the evaporated material. If you do not use these boxes, you can use crucibles, but then you will need a basket heater. You will need to have, for example, these crucibles that can be made of boron nitride or alumina, and you can or quartz, and you can just put these crucibles here in this filament, like this, okay? And then the current will pass through here. It will heat the crucible, and this thermal energy will go from the crucible to the evaporant material. Eventually, if it's high enough, it will melt the evaporant, and the evaporant will be evaporated, okay? And these are some examples of metal evaporants. You can have, for example, this kind of aluminum rods, this kind of copper or palladium pellets. Palladium is very expensive. I bought once a 5 centimeter disc of palladium, which was 3 millimeters thick. It costed something like $4,000, $5,000, something like this. Very expensive. And on gold, you can also put tiny bits of gold into the crucible to melt them. Okay, and so you can have an idea at which kind of wire you can use for the filament, depending on the crucible that you want to use. This is from a maker, which is what's the maker's name? It's Lesker Company. Okay, so this table was taken from the Lesker Company website. And so these are the crucibles. So the crucibles are actually these things here. So depending on the material of the crucible and the shape of it, you can see which tungsten basket you can use. Okay, and if it has 3 wires or 4 wires intertwined, because these filaments they have 3 or 4 wires which are intertwined, and you also can see how large is the current that you really need to have, for example, to reach a temperature of 1,800 degrees, okay? So if you want to make an evaporation of a material which has a melting temperature just below this 1,800 degrees, you really need to know what kind of power, either the volt times the current, or this is also given in watts, power, okay, which is required, okay? Some systems are more complicated. For example, you can have, instead of only one evaporation source, you can have 4. So for example, you can be evaporating 4 different metals at the same time, or 4 different compounds, or just using 2, or initially using 1, then using the second one, then the third and the fourth. You really need to have separate crucibles or separate baskets, because if you're using these kind of baskets, they become usually very contaminated due to the evaporant, and you cannot reuse them with different material. And these baskets normally use once, twice, 3 times, and then the filaments will become very brittle and they can break very easily. So you never use them more than 3 times. So this is my general rule of thumb. And you certainly do not use it with different materials, because then you'll have cross-contamination between chemical species, okay? And this is another example of an evaporation source, which looks like this. And these are some systems that you can use to make evaporation from different makers. We have a similar system here at our university, at the Department of Physics. I remember that I was in Fayoum in Egypt 3 years ago, and they installed a system which is very similar to this one. And I actually helped them choose the equipment. And now let's look at some of the disadvantages of resistive evaporation sources. So we're talking about the disadvantage of using these kind of sources here. Okay, so these kind of boats and crucibles. So it can lead to the deposition of impure films due to contamination. You can never say that you are not evaporating some elements from, for example, the filament or from the crucible. There's always a chance, if you're not careful by cleaning, and if you reuse either the filaments or the crucibles, you can have some cross-contamination. And also, the evaporation rate is very low for materials with high melting points. And so you have to check maybe to use a source or that can provide a higher energetic flux that can impinge on your evaporation source and increase this evaporation pressure. So regarding electron beam evaporation, which is the other process that you can use when you use a beam of electrons which are deflected by a magnetic field, in theory it allows you to deposit any material for any deposition rate. So due to the fact that the evaporating material is contained in a crucible that is water cooled, and I'll show you why, only the evaporant material reaches a high temperature, and so the surrounding material does not reach it. So the crucible does not reach this high temperature, and it will hinder its evaporation. Typically, it's in the form of an electron supply system. So you can have, for example, a tungsten cathode, and you need also an anode. The electrons emitted from the cathode are accelerated due to the potential difference maintained between the cathode and the anode. And in some cases, this potential difference can be around 20 to 30,000 kilovolts. So let's look again at this picture that I showed you a while ago, which had an electron beam source, E-beam source. Here you can see two electron beams being used for example, evaporating different types of materials. And it's interesting to see that there's a gas feed around the evaporation source. So when the elements are evaporated, they can react chemically, for example, with oxygen or with nitrogen. So, but let's look at the evaporation source. So this is how it looks like. This is where you put your pellets. So you can put your materials, okay, either copper, aluminum, palladium, gold, and you put them here, okay. And the surrounding material is copper. You use copper because the copper has a very good thermal conductivity, okay, as a metal. And so it will be very efficient for cooling this part because you only want to make evaporation for the material which is here inside this hole, this crucible. You do not want to evaporate copper. So underneath this copper plate, there is water. There's a water system here, water cooling lines that will provide a sufficient cool temperature so that you will not be evaporating material from the copper, but only here from the middle, okay? So, like I said, you need these cooling lines to cool down the copper part of the material. Then you have to have your evaporant material, which is put here in the middle. Then you need a cathode, which can be a tungsten wire, and you have to have, for example, placed around your chamber, you have to have an anode, okay? So where you can apply this potential difference between 2,000 and 30,000 volts. Then you need to, when the electrons are ejected from this cathode, from this filament, you need a magnet to provide this circular path to the electrons. And you have a very high energetic beam that will impinge in the evaporant source, will melt it, and will create this material vapor, which can be metal, or can be a metal oxide, can be a metal nitride, can be another type of compound, okay? For example, if you want to make titanium dioxide, you can have, you can do this both ways. You can have just titanium small particles, like titanium pellets, and then you need to feed some oxygen, okay? So that when titanium melts and evaporates, it will chemically bind with oxygen and react and form this titanium dioxide molecule, which will be depositing on the substrate. Or you can also have titanium dioxide crystals, which you can have here. The crystal can be brookite or anodized rutile crystals. And you don't need this reactive gas. You just use the electron beam to evaporate the material, and it will condense onto the substrate. So now let's see an example here of evaporation. I'll show you this small movie here, how an electron beam evaporator works.
An electron beam evaporator, a type of physical vapor deposition tool, is used to coat one side of a sample with various metals. Commonly used metals on this machine include aluminum, platinum, gold, chromium, nickel, copper. Once a sample has been loaded, the chamber will be closed. The chamber is then pumped down to a very low pressure. The machine then releases electricity through the filament. Several magnets are used to direct the electron beam from the filament to a crucible containing the target metal. The metal then heats up and begins to evaporate onto the shutter. This process can take several minutes. This is similar to a pot of boiling water or a hot stove. A sensor within the chamber is used to determine current rate of evaporation. Once the desired rate is reached, the shutter is open and the sample is exposed to the evaporating metal. The desired rate of evaporation and the amount of metal to be evaporated can be set under the deposition controller. Once the desired amount of metal has been evaporated, the shutter is closed. The pressure inside the chamber is then increased to atmospheric pressure, and the chamber is opened.
So you saw from this clip how an electron beam operates and provides thermal evaporation of some molecules or atoms, which will then condense into a film. Now, in this video, you notice there was a device which could measure the ongoing film thickness development, and it's actually we call it a thickness monitor or a quartz microbalance. And you can see it here. So you need to have a flange which will attach the measuring head to your system, and you need to have an oscillator, and you have to have a controller which will read out the thickness of the growing film. As input parameters, you have to know beforehand what is the density of the material which is being evaporated. And when you input the density here, then you can measure the thickness. For example, here you can measure 1.9 angstroms at a specific time. That is the thickness of the film. So basically, this is your deposition chamber that you have here. You have to have a vacuum system. Here you put your crucible. You can have a sword shutter so that you can, in the initial stages of deposition, you close the shutter so you will not. This is to prevent that atoms will reach your substrate or your sensor head. Okay. And when you decide to start producing your film, then you will open the shutter, okay? And as you open this shutter here, you rotate this manifold, then the beam will travel, or these molecules and atoms will travel towards the substrate, and they will start to condense in a thin film. I'm really sorry about the phone. I'm very busy now every day with a lot of people phoning me because of my responsibilities, and today it's a bad day for phoning. So this sensor will measure the thickness of the growing film. And how can we or maybe it's better to explain this way. How will this sensor head be able to measure the thickness of the film? So of the condensation of the material which is being evaporated and is being transformed into a thin film on the substrate. So it will make this kind of calculation here. You need to know something beforehand. So the thin film thickness, which can be measured in, normally it's in angstroms or nanometers, but you can also measure it in centimeters. Doesn't make sense because normally the films that you produce are angstrom size. You can make 20 angstroms or 20 nanometers, at most 200 nanometers or 2 microns in sputtering. You really don't make very thick films. Okay, maybe with thermal evaporation, you can do several microns, but you will never do something which is millimeters. It's too thick. It will grow too many stress inside the film, and the film will spallate, will not adhere very well to the substrate. Okay, so we're always talking about thin films. In generally, in true concept, thin films has to be less than 50 nanometers. When we're talking about with thickness more than 50 nanometers, then it's a film. And when we're talking about micrometers thick films, it's a very thick film. Okay, so the thickness of the film can be calculated by the density of these quartz crystals that you put here in this head here. Okay, so how does it work? It's like a balance. It's a crystal balance. It will be oscillating with a very high frequency. The frequency can be hundreds of kilohertz. Okay, so you have a crystal which is oscillating, okay, with a very high frequency with hundreds of kilohertz, and when it receives atoms, its mass will increase, and as the mass will increase, the oscillation will be damped. It will have a lower frequency, and you can correlate this reduction in frequency with the gain of mass. Okay, And since you know the density of the material which you are evaporating, then you will know the thickness of the material, providing that there is a good correlation between the amount of material which is being deposited on the sensor head and on your substrate. Okay, there is a tooling factor that we will have to use to correct this. Okay, so the thin film thickness is depends on the density of the quartz, which is these micro balances that we put here inside the sensor head. Okay, and when you buy these crystals, they already have specified what is what is the density of the quartz, and also what is the frequency constant that you also have to input here in the controller, so it can actually measure the thickness of your film. And then by knowing the frequency of the loaded crystal and the frequency of the unloaded crystal, which means F and Q are the frequency of the crystal after deposition, and FQ is the frequency before deposition. So if you know these parameters, then you can measure the thickness of your film. There's a more rigorous way to do this. Take into account not the frequency, but the acoustic impedance of the film material and that of quartz. And these EQ values for quartz should also be given here in the box when you buy these crystal macrovalence crystals. And so the formula is a bit different. It takes into account also the density of the quartz, the density of the film of the material which you are evaporating. This frequency constant also is included, and here and now you need not the frequency of the loaded crystal, but it's related to the period of the frequency, which can be easily derived. So, but depending on the geometry of the system, for example, if you go back here, you can see that when you open this shutter, the flux of atoms will go preferably in this direction, okay? So you will have a good coverage here of the substrate. But eventually some of them will hit the sensor, which is at an angle in respect to this normal direction, okay? But if you know this angle, you can use a tooling factor to correct here the correct thickness, because you know that the thickness here is different than what it's actually being produced here in the sensor, because since you have more atoms going in this direction than you have in this direction. But as long as you know these distances, this distance here, the normal direction, and also this is the distance from the crucible to the sensor and the angle that it makes, then you can apply this formula here. Okay, so Lm is the distance between your crucible and your evaporation source and your sensor head, and Ls is the distance between the crucible or source and the substrate. Okay, and these angles theta S and theta M are the angles between the evaporation source normal and the sample surface. If you're doing this perpendicularly, so this theta S is 90 degrees, as it is in this case, it's 90 degrees, okay? And this angle here it relates the angle between the normal to the evaporation source and normal to the monitor head. And if you introduce these two angles here, and if you know these two distances, then you have a tooling factor. For the case, imagine the simplest case is when you have the sensor here in the middle of the substrate, right in the middle, okay? And if it's right in the middle, then this equation is very simple, because these two distances are the same, one over the other is 1, and both of these angles are 90 degrees, and the sin function of 90 degrees is 1, and so you have a tooling factor which is 1, okay? And these are some cases for materials that can be evaporants, like rubidium, samarium, scandium, etc. And you have the density, which you have to input here into the controller, and also some values of the acoustic impedance that you need to input here on the formula to calculate the thickness. Okay. And so with this, I conclude this part of the talk regarding thermal evaporation. I really hope you enjoyed. And if you have any doubts, you can send an email, and or maybe we can perhaps manage a Skype or a Zoom meeting with you, and I will be more than happy and available to discuss with you and any doubts that you might have. Okay, thank you very much.